Hi, my name is Madelyn Broome, and I'm a fourth-year PhD candidate in astronomy and astrophysics, advised by Ruth Marie Clay at UC Santa Cruz. And the dramatic title of my talk is Supersonic Winds on Alien Worlds. But the more scientific version is modeling the supersonic winds escaping from exoplanets close to their host stars. So of the nearly 5,000 exoplanets that have been confirmed, hundreds of them are close enough to their stars that they orbit around them in anywhere between 100 days, which is the orbit of Mercury, to 1 day, taking just 1 day to travel around their star. So naturally, these planets are very hot, anywhere from 10,000 degrees Celsius, which is 17,000 degrees Fahrenheit, to a couple thousand degrees Celsius. And because these planets are so close in, they're heavily bombarded by X-rays and extreme UV rays. Now, these rays have the ability to ionize the atmosphere, causing it to heat, expand, and begin to flow outwards, flow off the planet as they escape the planet's pull of gravity. They begin to move so quickly, in fact, that they start to travel faster than the speed of sound in the atmosphere, becoming supersonic outflows. Now, sometimes these can actually strip an entire atmosphere away from a planet, leaving it just as a bare, rocky core with no atmosphere. But for the most part, planets just lose a small fraction of their mass. But the crazy thing is we can actually see these tails when we look through telescopes at these planets. We can see these flowing atmospheres off of these planets that follow the planet like a cometary tail. You can see here in this animation how the planet orbiting around the star drags its tail behind it, and when it passes in front of the star, it blocks out a portion of the light. And that's what we can use to detect these outflowing atmospheres. But the issue is, from those observations, we're not able to get the exact rate at which these atmospheres are outflowing from their planets. And that's really important to be able to understand the evolutionary histories of these planets, where they've come from, how they've evolved, where they're going. So what we've done is develop a publicly available, ultra-fast, one-dimensional model that has a brand new ability in this subfield of atmospheric escape, which is the ability to model incoming X-rays and how they interact with the planet, and also multiple elements in the atmosphere, which is very important because all of these planets should have more than just hydrogen in their atmospheres, just like how Earth has more than just hydrogen. So these can be used for a variety of exciting unanswered questions in our fields. We can apply it to see how we can observe these outflowing atmospheres, to see whether or not having more elements in your atmosphere is going to affect your mass loss rate. And it's ultra fast. And so a lot of folks are very excited about the ability to apply this to make hundreds of models all at once so that they can simulate populations of exoplanets or explore lots of other questions around them. So lots of unanswered mysteries that, thanks to ARCS, it is going to be possible for me to travel around, advertise, and really represent this code and push forward this science. Thank you.